Hello, I hope you have enjoyed the previous lecture. Lecture using chalk and board is a dying breed these days because teachers are getting more and more used to the high tech of PowerPoint presentations, and I thought that the giving chalk and board presentation would be somewhat interesting, and my students enjoy it. So let's continue with today's lecture. The previous lecture we covered the Hartree-Fock theory, and today we're going to go beyond the Hartree-Fock theories. And in order to go beyond, let's go back to review what we have approximated in the Hartree-Fock theory. So the approximation in the Hartree-Fock theories, we have three approximations we have made it from the lecture one. The first approximation is in the n-electron wave functions. We assume it is given by a single slat determinants. In other words, it came from a single electronic configuration. Okay? And usually, if we solve for the ground state, it is the electronic configuration for the ground states. The second approximation is in the molecular orbital approximations. And the molecular orbital approximation, we use a linear combination of atomic orbitals. The one way to addressing this approximation, we just including more atomic orbitals, higher order of angular momentums, atomic orbitals, and so on, until we reach the basis set limits, and that we'll cover in lecture 4. And the third approximation is in the electron repulsions potential operators. We introduce a centrifugal approximation. Right? So we will talk a little bit more about that. So when we do so, when we introduce these three approximations, what we've done is that we started out with the electronic Schrodinger equations of n-electron wave functions. A single differential equations is unsolvable. Okay? And when we do so, of three approximations in, we break the one n-electrons problem into n, right? And one electron problems, right? Fock operators are operated on the spin orbital I, given orbital energy chi-I and spin orbitals chi-I. So it's similar to the old, Oriental culture saying you cannot break a bundle of sticks at once. What you need to do is you're breaking a single chopstick one at a time. That's what we just did. Okay? So now let's take a look at, the errors come from these three approximations. Right? The way we do that, we define the term correlations energy. The correlation energy is the exact energy subtracted by the Hartree-Fock energy, or the error in the Hartree-Fock theory. So variational principle saying that, the Hartree-Fock energy is always above. So therefore, the difference with the exact energy is always a negative. So we know if we can improve our theory from looking at the E-core, right? There is two ways to deal with this, to calculate the correlations energy. One is to using the molar placid perturbation theory, or we using MPN. So molar placid perturbation theories, assuming that you get a pretty darn good wave functions and energy from the Hartree-Fock theories, leaving a small corrections that you can calculate and add it to it. Okay? The other approach is known as the configuration interactions, or CI. Well, CI said, okay, I'm going to add in contributions from excitations to the wave functions. Okay, so directly I'm going to addressing CI addressing the approximations number 1. Effectively, it accounting for both approximation 1 and 3. Okay, so let's go to the molar placid perturbation theory. Molar placid perturbation theory, MPN, as we know. Now, the key aspects of the theory saying that if an E0 and psi0 are the exact energy and wave functions of the Hamiltonians H0, which similar or approximate instead of the real full Hamiltonian, where the difference between the full Hamiltonians and the approximated Hamiltonians is small, then the energy and the wave functions of the full Hamiltonians or the real Hamiltonians can be expressed as sums of energy E0 and different order of corrections. The wave functions also psi0 and then added different order of corrections. Perturbation theories provide a framework for calculating these corrections to the energy and the wave functions. Okay? So, let's get back to it. The Hartree-Fock wave functions is actually exact solutions of these approximate Hamiltonians, which is the sum of the Fock operators. Remember the one electron operators that we just mentioned, a single stick, right? With the energy as the sum of the orbital energy. Okay, so that's fit right into the perturbation theory. Then we can say, well, in that case, but let's look at the difference between the real Hamiltonians and the approximate Hamiltonians. It's just the difference between the correct electron repulsions and the approximated by the central field approximations. So in other words, these are the corrections for the central field approximations, error in the central field approximations. Now, what interesting is the Hartree-Fock energy, okay, is not the E0, right? The sum of orbital energy, but actually it is the E0 plus a first order corrections. Here is why, right? So you have to go back to the first lectures to get back to where we apply the variational principle to calculating, to solve for the MO coefficients. Remember that we're introducing the central field approximations only when we solve the partial derivatives of the average energy over the coefficient equal to 0. It's because we cannot factor that partial derivative into the form that we can solve. So we did not introducing that approximations in calculate the energy, the Hartree-Fock energy. So in fact, the Hartree-Fock energy does not have this central field error. So let's see. Now, the central field errors have the potential of electron I, right? And the electron I's have experience of all the potential of all other electrons. Let's say electron J. Now, when I come to the term of the potential, central field potential of the electron J, well, the potential of electron J, all the potential which also including the potential of electron I. Well, that's double counting. Okay, so these terms have a double countings in there, and in fact, that errors, right? The first order correction you can prove is that is the double countings in the central field approximation, which is not introduced in when we calculating the energy of the Hartree-Fock theorem. So the energy of the systems, then the energy of the Hartree-Fock added the second order correction, third order corrections, and so on. And the wave functions is the Hartree-Fock wave function at the first order correction, the second order correction, and so on. So for example, that's the reasons why perturbation theory MPN starting at n equal to 2 instead of n equal to 1. So we start MP2, MP3, MP4, and so on. All right. So for example, at MP2, we can calculating the second order energy corrections by the formula and integrals of the Hartree-Fock wave functions we solve from the Hartree-Fock. The errors or the difference between the real Hamiltonians and the approximate Hamiltonians. So again, going back, that is these terms, right? The correct electron repulsions and that by the central field approximations. And the first order corrections to the wave function integrated in all space. So perturbation theory is providing the framework to adding corrections to the energy and the wave functions one at a time. It assuming that you having very good Hartree-Fock wave functions and the energy, which is pretty good. In some cases, the wave function, the Hartree-Fock wave function is not so good, then the perturbation theory is again may not be providing a good corrections. And in some cases, we do know that. The wave functions do have the term called spin contaminations in the open shell cases and so on. Okay, so this is just a brief overview, the framework of perturbation theory. So let's move on to the configuration interaction. It's easy to understand configurations interaction theory by using the example, a simple example, the hydrogen molecule. So let's take a look at the hydrogen molecule. We have two molecular orbitals, sigma and sigma star, and the ground states have two electrons in the sigma. Now, let's look at the single excitation. So I'm taking the beta to go into the sigma star, or I'll take the alpha to pop it over the sigma star. So both of these are single excitations. Or I can take both of the electrons excited to the sigma star orbitals, and this is a double excitation. So let's say the spin orbitals are chi1 is a sigma times the alpha, so it's representing the alpha electron in the sigma orbitals, and the chi2 representing the beta electron in the sigma, and chi3 representing the alpha electron in sigma star, and chi4 representing the beta electrons in the sigma star. Okay. So now let's look at this slightly determinant wave function representing these electron configurations. The ground state, so slightly determined, you can recognize chi1, chi2, slightly determined electron 1, electron 2. Well, single excitations in the case, for example, I'm taking the chi2, that means the beta electron. So this one, taking a beta electron to pop up here. So that means taking a 2, right? It go to the 4, so I'm stay the same spin, right? So beta from sigma go to beta and sigma star. So this is from 2 to 4, right? And the only thing is I do is I'll take the chi 2 over here. I switch to the chi 4. So now chi 1, chi 4, chi 1, and chi 4. Slightly determinant. Simple, isn't it? So now, for the double excitation, similarly, I will take both electrons, 1 and 2, right, in go to 3 and 4, right, go all 2 electrons from sigma to sigma star. So all I need to do is replacing 1 and 2 by chi 3 and chi 4 in the slider determinant. So this slider determinant representing the double excitations in the H2 molecules. So the CI wave functions is then writing as a weighted contribution of the Hartree-Fock ground state wave functions added all contributions of the first, the single excitations multiplied by these weighted contributions, added all contributions from double excitations, multiplied by their weighted contributions, and all triple excitations, all quadruple excitations to all orders, n order excitations, where n is number of electrons. Okay, in case of H2 molecules, we have 2 electrons, so we have up to double excitations, and that's it. That's the end. You see, we said that's all we have. So now it comes to the fact that these coefficients, weighted coefficients, are the unknown. And the way we determine that, we're using the variational principle, similar to the Hartree-Fock theory, right? We calculate the energy, the average energy, the CI. We take partial derivative of it with respect to all of these coefficients. We set them equal to 0, and we calculate their coefficients. Exactly the same methodology. Okay. Now, what neat is that the CI wave functions, by adding the contribution from excitations, is not only accounting for the errors in the wave functions of the Hartree-Fock, but also accounting for the center field approximation. How so? Okay, imagine this. Right? In the center field approximations, you are a blind person. You only sense the existence of other students in the classroom by the potential acting on your skin. Where they sit, they will send that potential on your skin. Okay? Now, if that students move to a different seat, you will be able to tell the difference. Right? So if another students are moving to all other, possible seat, and by comparing the difference in the potential, you effectively know where they are. Right? So in other words, it accounting by including the all possible excitations, you effectively accounting for the center field approximations, error in the center field approximation as well. The problem is getting very expensive. Okay, so it's very, very expensive. Computational, very expensive. So practically the way people do this is they truncated the CI by including to a certain number of excitations only. And for example, the CIS, they're including only single excitations, or CISD, they're including only single and double excitations. And if you, it can be proved that the electron correlation energy are accounted mostly from the double excitations. So therefore, if you include at least up to double, you can get pretty good for the correlation energy there. So now, another method that are similar to the configuration interaction, we call the couple cluster or CC method. So the CC methods, the only thing different is that the wave functions in the CC have this exponential, right, e to the t operators multiplied by this wave, the Hartree-Fock wave function. So these operators operate on the Hartree-Fock wave function. So now these exponential t operators here if we expand it in the Taylor series, is 1 plus t plus 1/2 t squared and so on. And t here is a sum of t1, t2, t3. It's just a different type of excitations. Right? It is an excitation operator. So for example, T1, if it operates on the Hartree-Fock wave function, it generates all possible single excitations with that weighted contributions. T2 operated on the Hartree-Fock wave functions, it generated all double excitations with their weighted contributions. So T2 operates all the double excitation term, T1 all the single excitation term in the wave functions. So it's kind of way, if it is full size, that would be the same. However, if we're doing for practical purpose, we truncated the couple clusters. So let's see, we truncated at single and double. So that means the excitation operators have only T1 and T2, single excitation and double excitations. Now, if you plug in e to the t to the Taylor series expansions, and you expand it out and collecting terms, you recognize it that 1 plus T1, T2, right? But then 1/2 T1 squared. Oh, I get an error. Okay? And the term of T2 times T1 plus 1/6 T1 cube is an effective, and so on, all the way to, right? So, and you recognize that, well, hey, 1 plus T1 plus T2. This is the same thing as CI single and double. Well, what is the rest here? The rest there is that it including the couple cluster, including the contribution from higher order excitations from what it knows from the single and double in the case of truncated single and double. So, in other words, couple cluster is more accurate than single. Couple cluster, single and double truncated couple cluster is more accurate than the truncated CI at the same level, or the same truncated level. For example, couple cluster single and double is more accurate than CI single and double. Okay, so I hope I introduced you to a variety of the different methods that we can go beyond the Hartree-Fock. These are the MO-based methods that we can use to improve the accuracy in our energy and the wave function. Remember, from the wave functions, we can calculate all physical properties as we stated in the quantum mechanics postulate. So the next lecture, I will introduce you on the density functional theory.